PhD in geology, so her talk is going to be about geology. How about now? Can you test?
Can you hear me now?
I can't hear you. Can you?
How is it?
I'm not going to talk when you're doing your presentation, so I think we'll be fine.
Anytime you're ready.
We're ready.
Okay. Greetings from England. I'd like to take the opportunity to talk to you a little bit about the history and history of subsurface geology. It's something that's really taken leaps and bounds in the last century because of the advent of something called seismic reflection. And we've been able to really map what's beneath our feet, including here in Los Angeles. So subsurface exploration has three main methods. The seismic methods are what I'm going to concentrate on today. There are two types of seismic methods. One is seismic refraction and the other one is seismic reflection. Seismic refraction basically is sending sound waves down into the earth and it's refracting or bending, jumping back off different layers beneath our feet, and it's being recorded at the surface, and that gives us some kind of idea of how many layers are beneath us and how thick those layers are. The seismic reflection method is very similar, but we're measuring how long it takes for the seismic waves to jump back off a boundary and back up to the surface of the earth. Some of the energy goes back into a lower layer and then reflects back from that layer, so there are many, many different layers that we can map beneath us. It will also tell us how thick those layers are, and there's no restriction on how many layers that we can actually measure. Seismic refraction, we can only really measure about 4 layers. Resistivity is basically the resistance or measure of how strong a material opposes the flow of an electric current. Different materials offer a different resistance, so we can actually map that resistance levels beneath us, and that kind of gives us some idea of the different layers. There's also magnetic methods. Magnetic susceptibility is one, but basically any kind of changes in the geology, if you have mineral deposits beneath you, it gives off its own magnetic field, and that perturbs, it makes a measurable local perturbance in the Earth's magnetic field, and we call this a magnetic anomaly. So today, because seismic reflection is the one that's most commonly used to map the geology beneath our feet, that's the one I'm going to talk about a little bit today. So reflections of waves generated by earthquakes have been observed on seismograms since the beginning of modern seismology. We've been measuring those the waves generated by earthquakes for quite a long time, since the 1800s. But this, in the 1900s, we were able to realize that we can use those seismic waves to map the Earth's interior. This tells us where our each layer is, the mantle, the crust. This was able to tell us exactly what we're looking at in the deeper part of the Earth and where those boundaries are. But last century we found out that we could actually generate our own seismic waves, and we could use these in a commercial way, particularly in the petroleum industry, and this gives us some kind of idea of where different layers are and where we can find the petroleum that we want to find, and also the minerals as well. We use it for both. So just a little bit about the history of seismic reflection. Ludwig Mintrop was a German mine surveyor. He actually first proposed seismological methods for exploration, and he first got his patent in 1916. So Reginald Fessenden was a Canadian inventor, and he was the first to actually conceive of using the reflected seismic waves to infer the geology. He filed a patent in 1917 while he was working on methods to detect submarines in World War I, but due to the war he wasn't able to follow up on that idea. So then we come to John Clarence Karcher, who actually discovered seismic reflections independently while he was working for the Bureau of Standards, which is now the National Institute of Standards and Technology, and he was working on methods of sound ranging to detect artillery. During the discussions with colleagues, he came up with the idea to use the seismic reflections in petroleum exploration, because basically anytime you have a layer that has a different density and waves travel through it in a different velocity, then we can actually construct where those layers are. Also, he was affiliated with the University of Oklahoma, and this helped to form the Geophysical Research Corporation as part of the old company Emerada. In 1930, Karcher left GRC and helped found Geophysical Services Incorporated, which is GSI, and of course we know this today as Texas Instruments. He conducted his first field test near Oklahoma City in Oklahoma in about 1921. I just want to talk a little bit about the three types of seismic waves, and I did mention that there are two different types of seismic reflection. One is seismic reflection and seismic refraction, and as you can see, we have the critically refracted waves which actually travel along the boundary between the two different rock types. You have a rock type at the top and a rock type at the bottom. Each one of those has a different velocity, and we use these refractive waves in seismic refraction, but the ones we're interested in seismic reflection are the ones that actually bounce off each layer. So the boundary between these two layers that have different velocities and different densities, it takes the time for the wave to travel down to the boundary and reflect back up to the surface. So the seismic reflection method basically can be used to map the geological layers and just give us an idea of what's beneath our feet. Now, it doesn't actually represent those layers. What it's telling us is that there is some kind of contrast at that point in velocity and density. Now, we can use two different types of wave sources. One is the shear wave source and one is the compressional wave source. And it depends on what kind of source, or we call it an active source, that we're setting off to send those seismic waves through the earth. And most of the time we use a source that uses compressional waves. And we can do things like use a simple hammer, which is usually about 10 pounds. We have a metal plate on the floor and we hit the metal plate with the hammer, and this creates a wave that travels through the earth, bouncing off each layer and back up to the recording geophones, which I'll talk about in a little while. Now, we can also use what we call a buffalo gun, which is basically an explosion. You dig a hole in the ground and you point the gun in and you shoot it, and that creates seismic waves. But obviously when we're in urban areas like Los Angeles, they're not very happy with us setting off guns. So we have to use the hammer in places like that for our shallow investigations. Just for slightly deeper, we use a weight drop, which is about 200 pounds. It's truck mounted and drops onto the plate. Again, that creates seismic waves. Here's just a quick picture of the hammer. As you can see, it's just a standard sledgehammer. There's the metal plate on the floor. And what we usually do is we hit the plate about 4 times so that we can basically add all those different reflections together, and then we can get a better, we can remove the noise much easier because it makes our signal stronger. So basically we can get some kind of idea of the geology, the subsurface geology, when we use the hammer from about 10 meters to about 60 meters depth. When we use the weight drop, here you can see the weight drop. It's truck mounted, it's about 200 pounds. Again, that just drops down onto the plate. We usually sum about 4 drops. And that can give us some information from about 50 to 500 meter depths. This is what we call a mini vibe, and this is about 7,000 pounds, and this isn't an impulsive source. This is just a vibration, and you can see here that the metal plate is dropped down onto the road, and it vibrates through a number of different frequencies for a certain amount of time. And the frequencies that you use depends on how deep you want to get. So we actually, with this particular source, we were able to get depths between 35 meters and a kilometer, so that's pretty deep. And then of course you have the sources for the deep seismic reflection, which they use mainly for oil and gas exploration. And this is a huge machine which vibrates at much lower frequencies, so the waves can travel deeper. And these surveys usually are between 300 meters and 7 kilometers depth, because we're traveling. So just a little bit about the land surveys, and this basically uses either a hammer, a mini vibe, a vibrosize, which is the large truck, and you set off your seismic wave at a point. These waves are hitting your boundary, which is your difference in your layer velocity and your density. They're reflecting back up to these geophones. So there will be a number of different reflections that are coming back to all of these geophones, and these are all summed up. And what you do is you take your source and you move down the line. So you will do it at this point and at each geophone. So you'll be able to sum all these different images together so that you can actually remove the noise much better and get a good signal. So this is just a little idea of the same thing that I was talking about, but as you can see on this diagram, you can see the little wiggles. And basically, this is the amount of time it takes for the reflection to get down to the boundary and back up. And as you can see with the yellow layer, it's slightly shallower. The time is slightly shorter. And with the red layer, it's slightly deeper, so it's a later time. And then the reflection that's coming back on the boundary between layer 2 and layer 3 is deeper again. And then the way they actually put these traces together is they tend to colour the peaks in dark. So when you sum these all together, it looks like a number of dark lines, and we'll see that a little later on in some of the examples I'm going to show you. So these layers basically have an impedance contrast, as I said before, which is a difference in the velocity and density between each layer. And again, you have the geophones there. Okay, so marine surveys are similar, but what you're doing is you're setting your source up off in the water, usually some kind of pressure source to create waves. And you can only have compressive waves because shear waves don't travel through water. And in these cases, what you have is a series of what they call hydrophones, not geophones, that are towed behind the ship. And the reflectors come back off each of the boundary up to the hydrophones. So it's very, very similar. And as you can see, these dark layers are basically the coloured-in peaks of all the wiggles. And on the right-hand side, you can see the interpretation of the data. So here we have the sea surface. Then we have sea level right there. Then we have the erosional surface beneath it, and you have a number of different layers. And then you also have some multiple images, which usually they can filter out when they're processing the data. So here's another three-dimensional section, although we're only showing 2 dimensions here. And again, each line represents a reflection. So basically, each line is a boundary. And the reflections come from the interfaces between the layers and with different seismic velocities and densities. The heavier the line is, the larger the contrast between the 2 layers. So there's a much bigger difference in velocity and density, and they'll give us these darker layers. Sometimes in a land survey, if we see the water table, that will sometimes come up as a very strong reflection. So once we have all our data, we have to process it, and we use a number of different things. We have to filter it out, There's a lot of background noise which has a certain frequency, usually around 60 hertz, so we want to filter out anything that might contaminate our data. We also have to make sure that we have some kind of common depth point, which would be on this particular section, particularly if the layer is dipping. And if it's horizontal, then we call it a common midpoint. And we make sure everything lines up with that when we're processing the section, so that our reflectors will be exactly where they should be. So here's just a picture of the seismic reflection profile. And this is where the data interpretation comes in. And as you can see, we have a number of different reflectors here. This is actually from the Nankai Trough in Japan. And I'm not sure if you can see this very well, but basically the reflectors here are all cut off. So we know that we have our fault coming in through here, which is represented by the red line on the bottom. And we know that all of our layers above it are folded. So this gives us some idea of where our faults are and where our folds are, and gives us some kind of relationship between the two. We can use this for, as we said, petroleum exploration, and where I use it myself is we use it in seismic hazards, because it's important for us to know where the faults are, and so that we can do some kind of hazard plan to take into account how many earthquakes, how fast the faults are slipping, where the faults are. And these layers are basically associated with some kind of change in character of rock type, or something with a different velocity or density. So I just wanted to go through a few examples, and as you can see, this is mainly petroleum industry data, because it's very expensive to collect, and we are then given it for academic or scientific use, and we can then come in and interpret this data. As you can see here, we have the folded stratigraphy above, we have cut-offs right in here, so we know our fault runs through here, and we also have another fault running through here because of additional cut-offs. So as you can see, they've drawn in a couple of different faults which we can interpret from this seismic section. So basically, the layers here are moving from left to right up the thrust ramps. And this is another example from the Niger Delta. And this is also a fault, but as you can see, this is doming up. And in this case, you can see the cut-offs of all the different layers really nicely, particularly this layer right here that basically comes into the fold and stops. Everything below the fault is horizontal. So this really shows us that we have this beautiful ramp cutting through the stratigraphy, and then we have a flat at the top, and the upper layers are being pushed up this ramp and just folding at the top because we've got nowhere else to go. Here's another example. This is from Argentina. This is actually a concave up, so this is what we call a synclinal fault bend fold. And as you can see, the stratigraphy is cut off right through here, and there is a slight change in the fault dip, so it's dipping more shallowly here and deeper right here. So that's why you see this fold as it comes up the ramp. So you can see the layers come to this point, and then they're basically being deflected upwards. Again, this is all data from the petroleum industry that we've been given to interpret the geology, or the structural geology. And here's another example. This is from the Tarim Basin in China. And again, you can see that all the layers are cut off above and below. And we have an interpreted fault right here. The layers come into the fault, and the fault stops there, and everything above it is just folding at the tip of the ramp. So you can see it makes this very nice dip where it's horizontal here, dipping here, and again horizontal here at the top. So again, and this is being dragged, also dragged by the fault itself. we call this a growth fault propagation fold. And here's one in Cascadia, Canada. Again, you can see these beautiful layers that are actually cut. You can see it very clearly on the uninterpreted section. This very clear, sharp reflector right here is this reflector right here, so they are being cut by this fault. So these are really nice sections where you can actually see the fault itself, as well as these beautiful reflectors. And this is, we see a number of thrust faults here, where the stratigraphy is just being pushed up the ramp and folding. So you have that slight diamond again here. And this is again from the Nankai Trough in Japan. And we call this a pure shear fault and fold because, as you can see, everything above it is just slipping on this layer that has no friction. So we have a number of different faults in here. All the black lines are faults, and all the coloured layers are our reflectors representing our stratigraphy that are basically being pushed up the ramp. So it's really nice that we can, I should say this is below the ocean floor, but it's really nice that we can get a pretty clear image or idea of how the stratigraphy is forming with respect to the faults beneath the surface. We wouldn't be able to actually have any idea of what was going on if we didn't have this seismic reflection method. And of course, Los Angeles, here we see downtown Los Angeles, we're surrounded by these majestic mountains, but the center of the basin looks pretty flat. And as you can see, this street here, it still looks pretty flat, but of course this is very deceiving because the Los Angeles River and the San Gabriel River have done a very good job of filling in all the different faults and folds that are beneath our feet. So it looks flat to us. So when we've had a lot of these large earthquakes, like the 1987 Whittier Narrows and the 1994 Northridge earthquake, it was a big surprise because we didn't know what was lurking at depth. Seems to be stuck a little bit. I'm not sure if the next one downloaded.
Do you maybe happen to have these on your desktop?
I can pull them up on my desktop.
And maybe we can see them that way.
Do you want me to? It's very deceiving when you see such flat topography in the Los Angeles basin, and yet we have these huge deep faults beneath us. And I don't know if anybody's actually taken a drive down La Cienega, but there's a number of oil derricks on the right-hand side, and that's because we have a lot of structural traps for oil. And there's, I do believe that they are drilling into the Monterey Formation, and there's a lot of oil beneath us because of these structural traps, and that's why we have access to a number of petroleum industry seismic reflection profiles across Los Angeles. These have allowed us to map these blind thrust faults that we've been studying and learn that they are a seismic hazard, and try to get some information for seismic hazard analysis to help us in our emergency services response for Los Angeles. And unfortunately I can't show you many of those pictures, But basically, that's what I wanted to talk to you about, and thank you very much.
So you have questions or?
So any questions?
We have a question. Let me get a portable mic.
Using the information you have, do you think there will be an earthquake in Los Angeles soon?
You know what? If I could predict it, I'd probably be rich. Maybe we're not at the point where we can predict these earthquakes. All we can say is that there are faults that are capable of producing large earthquakes. When they last produced an earthquake, and how often they produce an earthquake, but nothing is perfect, so they don't actually rupture in cycles of like 400 or 1,000 years or 2,000 years. As we know from the San Andreas faults, they predict it to rupture every 100 years, and the southern segment hasn't ruptured in more than 300 years. So we know this information, and it's as good as we can get, but of course we'd like to do better.
Thank you.
Based on what you know about the faults that,
Any other questions?
can you tell where would be a good area? Because you talked about how the carbon dioxide into depleted oil and gas in the subsea leaders. So can that help out with knowing where to put it?
Well, mainly the seismic reflection profiles do show you where the structures are that could be trapping oil and gas. And we're actually piggybacking off of their data. So if they probably have a very good idea of where all the depleted oil reserves are. I'm not sure if there are any in Los Angeles because I know they're still drilling, so there must be a certain amount. And I know I was speaking to somebody from Chevron, and I know they're actually using that method, I believe, in Louisiana. But other than that, I really don't know.
Any other questions? Alrighty. Well, thank you, Lorraine. That was